and joining the seminar. Just for you to know, this will be recorded. So if you want to make a question, whatever comment you would like to do, just please keep in mind this. If you would like to be recorded, yes, so keep it in mind anyway. Okay, so thanks very much for joining. This is the prediction modeling and machine learning seminars. We hold this once a month. It's last Wednesday of the month. So today it's time for our seminar. We are very happy today having with us Yiyang Ge. He's a PhD student in our department, the Biostatistics and Health Informatics department. And he has done a very nice job in using topological data analysis, trying to solve some different questions with the aim of enhancing the analysis of big data sets in healthcare studies. And he's presenting today, which is going to be the first chapter of his thesis that he's already submitted, and he's expecting his viva to be happening very soon. And he has called this first chapter and this seminar under the title, Using Topological Data Analysis to Assess the Quality of Imputed Missing Data. So we're very happy of having you with us, Yiyang, today. So when you are ready, we can make a start, and all the attendants will have a chance to make questions and comments by the end of the talk. Okay, so sorry, let's start.
Okay. Good afternoon, everyone, and thank you for joining us today. Today's presentation focuses on the method of TDA to evaluate the quality of missing value imputation. And our discussion will unfold in 3 parts. Please move, Raquel. And yeah, first up, move, Raquel. Raquel, please move.
Yes, 1 moment.
Yeah. First up is I will lay down the basics of TDA and the fundamental principles and the specific metrics we are going to need for our method. And following this, we will go into details of our approach, and I will introduce the pipeline we have designed. And after that, I will showcase the results from our model, and finally, there will be a conclusion part. Yeah. I will share some personal reflections on this method so we can start. Yeah. And firstly, TDA is a promising field come from the applied algebraic topology. It aims to provide a well-founded mathematical, statistical, and algorithmic method to analysis to visualize or exploit the complex political and geometric structure of the data. So the field is based on topology, a branch of mathematics, and in contrast with the more familiar field of geometry, the study of the shape of the space. But topology can be broadly defined as the study of only those shape properties that are unaffected by any continuous transformations. Such as stretching, shrinking, bending, twisting, the non-continuous transformations like cutting or gluing. Yeah, here's an example. Yeah, please see this torus. Yeah, it's surface like a ring door hold. Imagine if we stretch it horizontally, it does not change the fact that there is only one hole on the inside. Thus, the property is preserved despite continuous transformation. Another example is please see the right. Yeah, the door hold and the cup. In topology, they are the same. They are topological equivalents. So because the only thing we care is the feature of the shape. So in this example, it is the whole. So this is why we use TDA. We care about the feature of the data's shape. In other words, the topology method can track the underlying qualitative structure of the data. Yeah, so move, Raquel. And moreover, and topological method assumes that coordinate invariance. That means that the topological features are defined not in terms of their position on a coordinate system. It is in terms of their shape. This is a very important concept. Imagine you can rotating the shape in a coordinate system, but without change its feature of the shape. And now let's move to the next please. Let's move to the world of the data. According to Professor Carlson, the data has a shape and this shape has a meaning. This is why we use TDA. For example, the linear regression, a well-established statistical method based on the idea that the shape of the data is linear, where a line in two dimensions and a hyperplane in higher dimensions. And understanding the linear shape is key to understanding the relationship between dependent and independent variables. But however, the data may resemble many other shapes which are harder to understand. Please move, Raquel. Imagine, for example, the data points that split into three distinct lines at a single point, forming like a flare. You can see the example on the screen. So the TDA, please move, Rika. So the TDA provides techniques to describe these shapes by listing their topological invariants, like holes or cavities, cavities. And we mentioned before to investigate the meaning of these topological features in terms of the specific data problem. It is a complementary tool for standard machine learning. It is useful in some scenarios where the traditional algorithms might struggle due to the data complexity, dimensionality, or nonlinear relationship in data. But here I need to emphasize here is TDA is not a replacement for traditional machine learning method, but rather a complementary approach that can be used in conjunction with machine learning method to develop more accurate and effective prediction models. They can work together. So this next topic is we use TDA to help understand the data structure. First, we need this is a relatively complicated process. I will try to provide a very brief overview. First, we need build a bridge from the collected data to a space in which topological invariants can be computed. Let's take clinical data as an example. First, we need to define a measure to assess the proximity between any two data points. That is to be able to measure how similar two patients are given the information we have for them. As long as a distance can be computed between the data points, we will be able to apply TDA tools. We convert the patient data into a point cloud. The choice of the distance depends on a different scenario. For numerical data, for example, we can use the variance normalized Euclidean distance or the Minkowski distance. For categorical data, we can use Goward distance. And the second, to highlight the underlying topology of the data, we consider the construction of the continuous shapes on top of the point cloud. This continuous shape may very commonly be used graphs like simply complex or macro graph. We will talk it later. And lastly, we can build graphs on the point cloud. We are able to compute the persistence diagrams. It is topological signatures representing our data shape summary is very important tool in TDA, and we will talk it later. And now we know, starting with a finite point cloud and the following, I will introduce a two approach, construct graphs on top of the point cloud, the simplicial complex and the macro graph. And then we'll present the concept of the persistence diagram and see how a persistence diagrams can be derived from a family of the simplicial complex and how it can be derived from a single macro graph. And next is about simplicial complex. It is a higher dimensional generalization of graphs used in TDA to identify the new topological features such as circle or roid. It can be geometric or abstract. It is a set of the simplices that satisfy that certain properties. And a simplex is a generalization of a triangle to any dimension. Like, for example, a zero simplex is a point, and the one simplex is a line segment, and the two simplex is a triangle, and the three simplex is a tetrahedron, so and so on. And yeah, you can see a simplicial complex is then a set of such as simplices that fulfills as two conditions. The first one is if a simplex is in a complex, then all its phases are also in the complex. And the second one is the intersection of any two simplices in the complex is the phase of both simplices. These two properties allow the simplicial complex to be used as a sort of building block construct and analysis of topological space, and it has been used extensively in computational geometry and TDA. For example, in TDA, they can be used to capture the shape of the data and understand its topological features, such as connected components, holes, or voids. Next is mapper graph. Please move, Raquel. Yeah. Briefly, the mapper algorithm can reduce the complex data to produce a one-dimensional graph. This graph is mapper graph. So suppose we have a finite point cloud and can compute all distance between all pairs of the points within the cloud. Suppose we have a function called filter function. Yeah, it is an important function that assign a real value to each point in the dataset. And this filter function is one of the important filter. Yeah, we will talk later. And then the mapper algorithm can produce in 5 steps. First, we need to find the range of the filter function, and a second, and we need to divide this range into smaller and overlapping intervals. And for each interval, and find the set of the data points whose values are assigned by the filter function. And we also need a clustering algorithm to decompose each of the steps into the cluster. And lastly, and we represent each cluster by a node and connect nodes by an edge if the cluster intersects trivially. This is the shared data points. The mapper graph shows this shows a point cloud separated into interval with diameter by resolution and overlap by gain. So if you can see the figure, the resolution and gain are two important parameters when we perform the mapper algorithm. The resolution is the diameter of the intervals, and the gain is the percentage overlap of these intervals. So the choice of different combination of resolution and gain will directly impact the final mapper graph. Okay, next is about persistence diagram. After we can construct the graph based on the point cloud, we can now use this graph to compute the topological invariant. And one way to extract the topological information is considering a family of simplicial complex and coding the topological invariance in a two-dimensional diagram. We call this diagram persistence diagram. We can also identify the topological variance in a mapper graph and represent them by means of the persistence diagram. So there are two methods. The first is persistence diagrams for simplicial complex. But since the time limit and the first one is quite complex and it will not be used in today's method, so let's move to the second one directly. And please move, Raquel. Yeah. The persistence diagrams for mapper graph. Here I need to mention the rib graph first. The mapper graph is set to coverage onto the rib graph. So the rib graph is a mathematical object reflecting the evolution of the level set of the real valued function on a topological space that can locally resemble Euclidean space. From the macro graph, we can get the extended persistence diagrams by tracing up and down the read graph to identify pairs of critical points that mark the birth time and the death time. The birth time, this should be mentioned in the birth time is where the points appear, and the death time is where the points disappear. And so the birth time and the death time of topological features in the read graph. For example, please see this figure shows that the birth and death time for trunks, branches, and holes, and we will use it in this method to profile the topological structures of the dataset involved in the pipeline, to assess the missing value imputation quality. Next is the in bottleneck distance. It is an important metric for quantifying the similarity in this method. It is a fundamental metric used to measure the similarity between two persistence diagrams. We just mentioned each point in persistence diagrams corresponds to a topological feature with its coordinates representing the feature's birth and death times. The bottleneck distance relies on the concepts of the matching between the points in the two diagrams. A matching is defined as a bijection between the points of the two diagrams. The pairing points from one diagram with rows in another one. So to illustrate this, consider two persistence diagrams A and B. We identify all possible bijections between the points in diagram A and B, and including the options of matching points to the diagonal. The diagonal, like the line where the birth time equals to the death time. So matching a point to the diagonal is equivalent to not matching it to any point in another diagram. So for each bijection, we compute the maximum distance between the matched point. So please see this figure, and finally we have our bottleneck distance. So this is a very brief introduction for TDA, and of course TDA has many other important concepts such as persistence landscapes, but they are not used in today's method. So due to the time limit, I will not discuss it here. So let's move to the method. Missing value. Handling missing value is always a challenge that must be acknowledged in any data analysis task. High quality data pre-processing can significantly improve the efficiency of the data analysis work. With missing value handling being a key stage in this process. The occurrence of missing value in data attributes to various complex reasons, which can be broadly we can define it into three types. The first one is missing completely at random. Under this classification, the missing data is entirely random, and its absence is not contingent upon any variables. And the second one is missing at random. It's the likelihood of the data missing is unrelated to the data itself and solely dependent on the observed values. For example, in clinical research, males are more likely to miss follow-up. This is one of the examples for NAR. And lastly is missing not at random. It's missing data is intrinsically related to the variables that it contains. For example, the high income individuals refusing to disclose their saving, like it could be an example. And our method will focus on the MCAR and MAR. Next, I want to mention about two previous research. Please move, Raquel. Raquel, Raquel, please. Okay. Here, I'd like to mention some previous research that use TDA to assess imputation quality. First, sorry, can you go back? Yeah, this one, yeah. In 20, in 2021, a team introduced a dashboard using the mapper algorithm that users can visualize both the presence of the missing data and the underlying topological structure of the complete and imputed data. This method describes the potential bias in data distribution caused by the imputation method. Further helps users to striking a balance between information loss and noise that arises when choosing between low and high missingness threshold and post decision making. It is fantastic dashboard, but it is bit pity. It's designed specifically for proteomic data, the numerical data. So if your data is categorical data, it may cannot help. And another research, Raquel, please. Yeah. In 2018, a team proposed a new methodology as TCDM, which used TDA to assess imputation quality. Their approach addressed missing values under MCAR and MAR by visualizing the underlying topological structure of the data with aim of uncovering hidden patterns in interrelated clinical outcomes where micrographs extracted from data. This methodology computes the similarity between the micrographs of complete case and imputed data using pairwise distance. The higher the similarity, the higher the imputation quality. It is a very nice method. It quantifies the similarity, allowing users to achieve the quantifiable comparison results. But the pity is we cannot review the process. The pairwise distance used in this method is spectral distance. The team does not clarify the definition of this distance and why they choose it. And they did not provide any calculation of functions or code script. So we have no way to verify. But based on the theoretical bias of the micrograph and suitable concepts of the distance between the micrographs, considering spectral distance could be misleading, as the micrograph might be affected by a noise in data, and this would also affect the distance calculations. And we can move to our data. And our method use study. The data we use in study. The study was prospectively designed to assess the efficacy of different treatment options for MDD patients. It was the largest and the longest study ever conducted to evaluate the depression treatment. The study was segmented into 4 levels, level 1 to level 4, with each level testing a different medication or combination of medications. And the primary goal of each level was to determine whether the treatment used could effectively manage the MDD. Those who did not achieve remission could advance to the next treatment level. So in our analysis, we focused on level 1 data, which involved the testing participants solely with the CIT. CIT. Please to the next page. Due to the time limit, I will not go into the details of the data pre-processing process. It's a bit complex. So just in summary, after data pre-processing, our study dataset has 1,528 observations and 62 variables, and including 56 categorical and 6 numerical variables. And yeah, most of the variables are categorical. And there are 11 variables with missing values, with the highest proportion of missing is around 25%, and the lowest is below 1%. Out of the total observations, the 744 complete case without any missing values, and 784 observations need imputation. And let's move to the pipeline. So our pipeline contains two parts. The first is we need to construct a macro graph, and the second we perform a permutation test. So initially, we will compute a series of macrographs for both complete data and imputed data, complete case and imputed data, and a range of the parameter combinations. And next, we perform a permutation test for each parameter combinations to test the hypothesis that the underlying topological structure on complete case is preserved after imputation. So for the purpose of the comparison, we will employ an alternate imputation error estimation technique, which from Dr. Beck, I will introduce it later. I will to discuss the results and to determine the feasible of our pipeline to assessing the imputation quality. And next, yeah. So we construct the macro graph. Yeah, so remember we mentioned before we need to choose the distance to build a macro graph. So the distance we use is scalar distance. Other distance like Euclidean distance is used to calculate and construct the distance matrix for continuous variables, and the correlation is commonly used to calculate the distance for categorical. For our data, over 90% is categorical variables. We choose to use scalar distance to construct the distance matrix. And the Gauss distance is this similarity measure applicable to categorical, ordinal, or internal data. And the most important thing is it is good at handling the mixed data type. So one of the properties of Gauss distance is scale invariance. By scaling all variables to have a range between 0 and 1, it ensures that the measure is not dominated by a single variable due to a differences in scale. And next is the filter function. We select MDS it is a valuable tool in topological data analysis due to its ability to simplify the complex and high-dimensional data into a more interpretable and low-dimensional space. It is also can preserve the distance or relationships between the data points. And in fact, we tested multiple functions to select a filter like PCA or kernel functions. So our choice of MDS is based on several reasons. However, due to time limit, I could not go into the details. If you're interested, we can discuss it further after the presentation. And next is we need to choose the parameter include resolution and gain we mentioned before. We also need a clustering algorithm to decompose a set of the data points which have already assigned by the filter function. So we test the wide range value of the resolution to avoid missing the essential data structure information. So you can please see the table. This is the range of the resolution and the range of the gain. About the clusters, we use DeepScan. Yeah. The main reason is when handle the dataset, the Gauss matrix was used to perform MDS as a filter function. The method allowed for effective dimensionality reduction while preserving as much of the original similarity structure as possible. Given that these conditions, DeepScan, due to its classification as the distance-based clustering algorithm, it has the advantage of flexible and making minimal assumptions about the structure of the data. It is well suited for the data transformed by MDS, as they can effectively handle the potentially non-convex and complex cluster shapes that might result from the MDS projection. Additionally, considering the MDS can wrap space in nonlinear ways, and DeepScan is a good choice due to its lack of assumptions regarding the geometrical shape of the clusters. And still, it is not the only reason we test multiple clusters here, like k-means and a collaborative nesting. Yeah, so still, if you're interested, we can discuss later. And next, we need to move to, so the mapper graph help us to account for the topological data structure of a data set, and they serve as a good tool for comparing the topological similarities between two data sets. So in our method, we seek to explore the topological similarity between a dataset made of the complete case and imputed data. Extracted topological information from data and can be represented in persistence diagrams, which generated from the mapper graph. And the bottleneck distance is a fundamental matrix in quantifying the similarity between the persistence diagrams. So once mapper graphs are derived from both complete case and the imputed data, we can use bottleneck distance between the associated persistence diagrams to quantify their similarity. This is the key point. And we can move, please. Yes, and so let's move to the pipeline. Our pipeline has 5 stages. And stage 1 is a hypothesis definition. Yeah, we hypothesize that the topological structure from complete case and imputed data is the same. Let's denote that D as the bottleneck distance. And you can see our H0 and H1 here, and means this means the hypothesis is the topological features from complete case and imputed data are not significantly different after imputation. The selected imputation technique restores the data with missing value in an appropriate way, as it preserves the topology in data. And the stage 2 is please move. Stage 2 is we can compute the test statistic. We compute an estimator for the bottleneck distance between the extended persistence diagrams for complete case and the imputed data. We consider the different topological features, connected components, up branch, down branch, and loops. We computed the bottleneck distance on each feature separately, and then select the maximum distance as our value for the bottleneck distance. And and the stage 3, please move. Stage 3 is that we can run a permutation test now. This stage used to help us to investigate whether the quantified similarity, the distance from stage 2 is statistically significant following the hypothesis test formulated in the stage 1. This stage has 2 parts. First is subsampling. We subsampled 100 subsamples extracted from the complete case and imputed data, respectively. And each subsample is selected at random and has the same size as 70% of the complete case, the sample size. And group A is made of subsamples from complete case, and group B is made of subsamples from imputed data only. And the second part is the shuffling. We grouped the samples in group A and B and forming a total of 200 subsamples and then shuffle them. randomly reassign A and B labels to each subsample. This resulted in two new groups of 100 subsamples each, the new group A and group B. And let's move to the stage 4. Yeah. Now we can compute the p-values and adjusted p-values. We built the macro graph for each sample and the extended persistence diagrams. And now we computed the Bosnian distance between pairs of these diagrams. The two groups have 100 subsamples each, and 100 Bosnian distance were computed. This way, we generated the null distributions for the distance parameter, and this is the formula. You can see the screen. This is the formula for the p-values. And the B2 is the number of the distance that's greater than or equal to the test statistic. And then we also need to compute the adjusted p-value. Adjusted p-value are used to maintain the statistical validity of conclusions when performing a multiple statistical test simultaneously by controlling for the increase in the likelihood of the false positive. So for this adjustment, we employed the BH method. Yeah, this is designed to control the false discovery rate, which is the expected proportion of incorrect rejections among the rejected hypothesis. We set Q value as 5%, and it means that the test is significant at an FDR level of 5%. And the last stage was, please move, Raquel. That stage is our conclusion. We selected the 5% as the significance level, and if adjusted, the p-value was higher than 5%, means that under the assumption that two samples, complete case and imputed data, come from the same population, the null hypothesis cannot be rejected. And the difference between the topological structure of the two samples is not statistically significant. In other words, we can conclude that this imputation quality is high. And otherwise, if the p-value is below 5%, the difference in topological between the two samples was considered statistically significant. We can conclude the imputation method is not preserving the topology in the data and may not be a good one. So let's we also need please move Raquel. Yeah. Well, we also pick another method to validate our findings and conclusions. This method is from Dr. Beck and estimates the imputation error through the simulation of the missingness patterns in complete case. And users extract all instances of the missingness patterns from the input dataset and replicate these patterns in the complete case. And after simulation, the complete case dataset incorporates the missing values which can be imputed using methods like KN. So given that we know both imputed values and the true values in the complete case, so we can compute the actual imputation error. And next, their pipeline and the actual imputation error can be used to compute the estimated imputation error for the entire input dataset using the different imputation algorithm we want. So it is a very brief introduction of his method. If you're interested, you can read his paper. And please move, Raquel. So our imputation method we use is KNN and mode imputation, less frequent and random noise. Yes, it's very common. So the first two methods are very common, and while the latter two are used for, the later two are used for comparison. So for KNN, the k neighbors we use is the square root of the number of the complete case is 27. Yeah, by the way, for the very few continuous variables in the data, we use median. And let's see our results. Yeah, please move very cool. Yeah. So let's see the estimated error first from by using Dr. Bake's method. Please see the table. The results are expected. Yeah. The lower the error, the better the performance. We can see a clear difference in effectiveness of each imputation. The KN imputation shows the best performance and followed closely by the mode imputation. But for less frequent and random noise, it's bit worse performance. So it's as expected. And please move, Raquel. Yes, this is our adjusted p-values. Let's see, since the full results are too long, so I only show the top 20 adjusted p-values here. The results are reported for the full imputation, and our focus lies in the count of the adjusted p-values that fall below 5% for each method. The results shows similar to Dr. Bake's method, with KNN outperforming the other method, and in terms of topological data structure preserving. Yeah. So for the KNN, totally 48 adjusted p-values and only 2 fell below 5%. This mean only 2 parametrizations showed a significantly different topology between the complete case and imputed data. And the mode imputation showed slightly lower performance with 6 value below 5%. But for less frequent and random noise, it's a bit worse. It's 10 values and 12 values respectively below 5%. These results are as expected. So provide the conclusion based on the metro validation between TDA method and Dr. Bake's method. And next, I want, please move, Raquel. Yeah, next, I want to show you something interesting, the mapper graph. Let's say the first case. In this case, we can see that KNN has the smallest bottleneck distance followed by the mode imputation. Yeah, you can see the table. Yeah. In contrast, the less frequent and random shows the larger values, almost twice as large as of KNN. We know that the smaller the bottleneck distance means a higher structural similarity between two datasets, implying a similarity between their macro graphs. So you can see KNN performs the best in terms of the features such as branch and arm, and mode imputation shows similar branch features. Yeah, but though there are some differences in overall structure, if we only based on virtual perspection, the difference between the macro graph of less frequent and the random imputation compared to complete case are most obvious, but this is a typical case that you can get valuable information based on your eyes. But for the most case, visual information is very limited. For example, let's say the second case. Yeah, please move. Yeah. And the second case, we can say that KNN as the method with the smallest bottleneck distance, but the distance for the other three are similar. But in this case, it is a bit hard to judge the information you need with your naked eye alone. You may think that random is similar, yeah, but it's also challenging to determine that KNN performs the best based on your eye. And the third case, please move little. Yeah, the third case is similar. You may judge that random performs the worst by your eyes, but how you judge other three by your eyes. So actually, vision is just a rough reference, and we cannot make final judgment based on it. Although it can provide recommendations for decision making or information discovery in some cases. So I think an advantage of our method is that we quantify the concept of the similarity. And when we discussing or making decision, relying only on vision may not be entirely reliable. So, however, when the concept is quantified, we have substantial evidence for comparison. So, is by comparing the structural features, we might uncover some hidden information. This has a positive impact on the imputation of MNAR. So, but it also requires the user to have professional knowledge and experience. Yeah. And then let's move to our conclusion. Yeah, missing value imputation is challenging work, so sometimes executing the imputation method was not enough. We also need to evaluate the quality, and thus using a powerful data structure mining capability of TDA to evaluate was considered. So I think the advantage of a method is puts the emphasis on the data structure and the data shape, which is a novel approach, and I think, and our method can handle the mixed data types. Yeah, not only focus on numerical data. And the third one is it does not require introducing a missing value into a complete case. But I have to say there's some disadvantages, and please move. Yeah. The first one is dimension into 100 subgroups appeared inadequate, may causing some extreme p-values exist, and the total number of adjusted p-values seems not enough also, because more subgroups mean that more combinations are tested and more micrographs are incorporated in the calculations, which can effectively reduce the impact of some extreme case. However, correspondingly, a large number of the subgroups could lead to a significant increase in computational costs, which requires a user to consider very carefully. Another issue is optimize the parameter selection. I think this is also a drawback of TDA. It requires users to have some extent of expertise in this field. And otherwise, parameter selection can be quite challenging for users. It is a very big topic if you pick a small part. Resolution and gain, for example. Balancing these two parameters with an acceptable range was necessary to optimize the extraction of the topological structure information. Resolution is the diameter of the intervals. If set to big, that is, each intervals are large, and the analysis could become too coarse, and significant topological features, particularly those existing on a smaller scale, risk being overlooked. So the topological summary could be oversimplified and missing key details. And conversely, if resolution was too small, the analysis could turn exceedingly detailed, and this could lead to overfitting to noise in the data and detecting the topological features that were not truly significant, but merely a product of random variation or just error. So the resulting topological summary could be very complex and difficult to interpret. And similarly, gains is the overlap among the covers. The choice for this parameter would be limited, typically set between 10% to 40%. It was generally safer to test all values between 0.1 to 0.4 by using parameter combination. So what I want to say is, although we have designed a pipeline, it is challenging to provide clear recommendations for parameter selection, because this requires users to determine to determine the parameter choice and value range based on their own data. Different data, different filter function, different clustering algorithm will lead to different choice of resolution and gain. In fact, the TDA does not yet have a wholly universal parameter selection scheme, and although some work has been done too. Essentially, users must choose the parameter based on their understanding of the data or systematically testing the multiple approach and the combinations as we propose in this presentation. In positive side, users have more freedom to adjust the parameters. However, it is important to keep in mind that the trial and error cost is also high, and handling data with complex computation requires a significant amount of time and resource for each trial. So, TDA has constantly struggled with the need for high knowledge and step cost of testing multiple parameter values. But we believe that TDA would hugely benefit of having a better defined guideline and how to set the general parameter values. Yeah. And the last one is about our software. We use Python and in several open source packages. Yeah. And for Baker's method, we use R languages and and two packages. So this is the end of my presentation. If you have any questions.
Yeah, thanks very much, Yiyang. That was really excellent, very interesting, very complex as well. So if there's anyone with a question, yes, please, you can raise your hand, Ling Long. So feel free to ask. Thank you.
Yeah, hello, can you hear me? Thanks for the talk. I have lots of questions actually. So I would like to start from the last one for the parameter selecting. And I'm not sure whether you have tried use the auto machine learning framework to select your hyperparameters. I mean, even the resolution rate or other parameters. Because as far as I know, the auto machine learning framework, or you can use the famous NNI package from AWS or some big company. It's very useful, and it can help people to select your set of parameters. Have you ever tried that? Oh, it's not works for your TDA master.
Yeah.
Yiyang, could you hear the question?
Sorry, I cannot hear clearly. Sorry, could you type your questions? Sorry.
If not, I can write it for you. I can read it for you if you prefer. So I think that Ling Long was asking about if you were trying some methods, some existing methods that are already put out to estimate the parameterization of the mapper, as for example, using the MMI package. Have you used this method, so you anticipate that this could be an advancement for your work? The auto ML framework.
Yeah, just auto machine learning, and this kind of pipeline just trying to help user to automatically select your hyperparameters.
Yes.
Have you chosen, or have you thought on using this framework, the auto machine learning framework, Yiyang?
So sorry, I can only the voice seems frozen. Can you just type some few sentences in the chat?
Yes, so Ling Long was already typing this for you. You can read in the chat the name of the auto machine learning framework. This is a framework to estimate the parameterization of your machine learning models, I guess. So is this being used on the mapper graph as well, Ling Long?
Sorry?
Oh,
yeah, it can be.
I can see that you say that about machine learning framework. Use automation framework to automatically select. Currently, I don't think so because based on my experience, you need to understand your data very carefully, and you need to you need to know the structure of your data, and you need to select the um, a distance and the appropriate clustering algorithm, and especially a good filter function. And all of this will influence on the selection of the resolution and gains. And this is this is what I want to say in my last part in the conclusion. Is it is a bit hard for users who do not very familiar with TDA to select their parameters. Yeah, this could be a disadvantage. So currently is the parameters. I don't think it can be selected automatically with some framework or by machine learning. Yeah. Yeah.
Okay, there's another comment by
the
Ling Long. You can read it in the chat.
Yeah,
Okay.
the cost or cost you have under that kind of a platform, do you use that? How long it cost to? Yes, there's the for my work it's running over 72 hours for the model, but it's also depend on your power of your CPU. So this is why I say to balance your computational cost. For example, if uh, we select the 12 resolutions and 4 gains and just one clustering algorithm. If you test, for example, from range from 1 to 100 resolutions, and you pick 5 clustering algorithms, and you use 1,000 subsamples, for example, and this combination cost will increase very high. Uh, yeah, so this is why I say the user should be careful to balance your computational cost. Yeah.
Okay, the second question was by Lei Luo. Would you like to make the question yourself, Lei, or would you like me to? I can read it in the chat. If not, I'm gonna read. I think that it's about the computational cost.
Yeah.
I think that you already answered this in some way. Yeah.
Your own computer or some site. Yeah, my work is to use my own computer. Yeah, if you can use other powerful computer, it should be faster, I think. Yeah. Another comment is since that TDA distance would not
No,
work
sorry, Yiyang. There is a first question by Diana before. I can read it so that everyone can listen. So is there any way to understand which predictors are imputed better than others?
I can see. Yeah. The only way to understand which predictors are imputed better than others. The way to understand which predictor what do you mean is which predictors are imputed better than I think uh I think this question could lead to my chapter 2. What do you think, Raquel? Yeah, maybe we can build actually both. What do you think? I think this question could lead to my chapter 2. We can build like clustering and build a XGBoost model to to say the feature importance. But in this chapter, in this method, we the main purpose is to assess the imputation quality. So in this method, we don't have we don't design the code to yeah to to say the which is better than others. And the second one is how metric dependent your results for metric dependent, and or you results what you mean metric.
So I guess that this means that instead of using the bottleneck distance, if you have used any other distance, if you think that the results would change.
About the metric is this metric, we select this metric very carefully because it is a very fundamental metric to to quantify the similarity between two persistent diagrams. And for example, the paper I mentioned before, they use was the spectral distance, but they did not provide any definitions, and we do not know what is that. So we, according to the Professor Calson's paper, and we select these metrics very carefully. So for me, I think we will keep use bottleneck distance.
I think that maybe you could follow the discussion with Diana later on, because there are many questions from her. So that's perfect, because I guess that Diana was very much interested in this. There are other two questions. One from Johan. Maybe we can move to that one. Has this approach been tested on imputation when number of variables is quite big, from 1 to 10 million, as for example in genomic data?
Yeah, I can read from sorry. I just read this one by one, sorry. So from then I said the same statistical distance will not work for we mainly focus on MAR and MCAR, but as I mentioned before, is if we use this method can help you to find some hidden patterns in the MNAR. Can provide you some valuable information, I think. But we cannot say this works completely for MNAR. So and next one is also not you only compare the imputation method. Okay. Why those examples are not covered? Just from Ling Long. Yeah, this the imputation method. Yes, we designed this pipeline to test it works. So we pick the KNN, and mod imputation is very common, and we pick the less frequent and the random noise. It's very as a comparison method. So the aim is we want to test this works. And another thing is over 90% of our data are categorical variables. So we use KNN, like KNN and mod information, mod imputation. And that's only 6 variables in our data, continuous variables. So we just use median to impute the missing value. And there's very, very few missing values in the continuous variables. And from Johan has the approach being tested in imputation with number of you mean the very high dimensional is no, we just test on the study, and we plan to test on other like genetic. Yes, but we have not tested on the high dimensional data. Next question from Linglong is for rows clustering. As far as I know, is Raquel and Gibson are all sensitive to imbalance the data. the TDA method to have any risk due to how to say, because the TDA is this is focused on the data shapes, the underlying structure of the data. So we the imbalance is will not a big problem in this method. Or what do you think, Raquel?
That we are not using the outcome here, and normally imbalanced data is because of the outcome, right, Yiyang? So what kind of imbalancement were you thinking on? So the missing data.
Yeah, typically a lot of, especially for clinical trial, once we have the missing problem, we always have the imbalance problem as well. And if for any imputation method, if you do not consider the imbalance property well, it will lead their final imputed data quite affected by the data distribution, quite difference between different groups because they're imbalanced. So as far as I know from this talk, the TDA method trying to evaluate the imputation quality. But how about if the data itself is imbalanced and those methods, some of them may care about the imbalance property, some of them may not, and their imputed data, the quality will be also different. So that's my only concern about that.
Yeah, but I think that this should be not run as a pre-process step in the data, but this should be embedded within the validation of the machine learning algorithm when you test the quality of the method. So everything that should be extremely computationally expensive. So, but the ideal scenario, maybe you would agree with me, would be to embed this in the loop of the validation of the method, so that when you impute the data separately between training and test, you also test there the quality of the imputation method, and you make the selection of the best method that is showing the best quality, right? And that would be, if you do this that way, and you are treating the imbalancement of data also in the same loop, embedded on the internal validation, let's say K-fault or nested or whatever internal validation you are running, they should be preventing the effect of the imbalancement of data. I agree this could not be done in a separate step, in a pre-process step. It should be embedded in case of imbalancement. So I agree with you on that.
Yeah, and maybe another part, another thing like
this should be, sorry, this should be really the last question because we are now 11 minutes over.
Oh, sorry for that.
5. No, it's okay. So last question from Ling Long, and we will finish. Thank you.
Okay, sorry about that. So the imbalance will not only happen between different groups, I mean for the positive group and negative group, but the imbalance situation will also happen for different features. For example, some demographic features, some laboratory features. And I also wondering, like you've mentioned, most of your data is categorical data, a categorical feature, and only 6 numerical feature. And I'm just wondering, like, even within the categorical feature, if their distribution is quite different, or if the numerical feature, their distribution also very different, will this evaluation method still works?
Yiyang? In principle, I think it should work with Yiyang, isn't it? Because you are just trying to evaluate the structure, the topological structure, and in principle, you should mimic this between the complete data and the imputed data. So in some way, you have these different distributions on the complete case. You should be mimicking this in the imputed data set. And so the topological structure, the preservation of the topological structure should be showing that.
Sorry, are you talking to me? Sorry, still my network seems something wrong. I just can hear a few words from you.
I'm sorry. I think that it was cut. I think we will need to leave. Ling Long, you can stay in touch with Yiyang, I think.
Yeah, thank you so much. It's okay from my side.
Thanks to you. was very interesting. Thanks very much for all your insights. Thanks everyone for joining, especially to Yiyang. I know it's hard to present these things, and we really hope that you will be very lucky on your Viva coming up very soon. So thanks very much, Yiyang, and thanks for your excellent talk. For the next talk, so I will wait for you here, guys. It will be on the 29th of November. It will be Taru Sorsa, who is an MSc student on the health psychology MSc at the IOPPN, and she will be talking to us on her investigation on investigating medication taking behavior in breast cancer survivors under complexity. This will be on the 29th of November, as I said, from 3 to 4 here online. You will receive the link in due time. So thanks very much. Thanks for joining, and have a lovely evening. Thank you.